We have Sonia, a PhD student from ETH Zurich. She's a PhD student in Julia Vogt group, working on interpretability and learning representations. And well, Sonia, the floor is yours, and bring us to this journey.
Thank you so much, Pietro, and also thank you so much for organizing this initiative. It's super nice, and I'm really looking forward to the talks. Today, I wanted to talk a bit about concept-based models for interpretability and learning representations, and mainly touch upon different aspects or works we have contributed that I think kind of are helpful to get a nice overview of challenges and future lines of research in this concept space. So first of all, let's see if it works. Yeah, the motivation behind these concept-based models by interpretability in general, everyone in the audience most likely knows, but I wanted to briefly point at it. It's that currently there's a widespread of opaque models, and this raises a need for understanding. And this is especially important in high-risk domains. So what is this interpretable machine learning from my point of view and in the view of this presentation, in comparison to, let's say, what explainability would be more hinting towards, is that we have some input data. And from this data, we might have some understandable or meaningful features. And all of these are passed through a white box model. What does white box mean? This means that we actually get to see what our features or our data is doing to then get an interpretable decision. Within this scope, I will now focus on concept bottleneck models that I believe there's also some upcoming talks in the seminar that will be touching upon this. So in a nutshell, they are neural networks or machine learning models that rely on high-level human understandable concepts. In this case, it's C, the yellow part in the middle, and have specific properties. So they are interpretable, meaning from some input, I get these concepts and then a target, and therefore at inference time, I get to see what concepts were triggered. And this also allows these models to be intervenable, because you can actually, at inference time as well, modify your concept, in this case, C prime, and get an updated prediction. However, these models have certain limitations, some of which are that they assume that, or the base model assumes that these concepts are independent. Moreover, there is a constraint on the bottleneck, meaning you need to pass all your data through this concept layer and then predict the target. Therefore, your architecture is a bit limited. And also it needs annotation that is quite expensive at training, so because you no longer need your pair of X and Y, but also your intermediate concepts. And finally, it assumes that the X and the Y are independent given the concepts, meaning all the information to predict Y passes through the concepts. And since this in the real world is not usually the case, it leads to some information leakage. For this, there's been literature adding residual layers to allow for this flow of information. Why am I introducing this now? Well, today's agenda is to actually go through some papers that tackle some of these limitations, as well as some extensions or applications of the concept bottleneck model. The first one I'm going to be talking about is learning a multivariate distribution. So given the limitation I mentioned that all the concepts were independent, we want to try to model them in a multivariate distribution fashion so that we can kind of go beyond this assumption. And for this, we introduced the stochastic concept bottleneck model. What happens, or what are we actually, apart from modeling it to improve interpretability, we also want to be able to intervene of these concepts, right? So I'm going to now motivate why we would need this distribution. So let's say the concepts here are the head and the body. And now I say, I'm going to modify or intervene on the head, and I'm going to say fish head. In the real world, most likely, this is not going to happen. And what you would really like is that by changing the fish head, your prediction goes into fish. So the original CBM, they would not allow for this. But if we now model all of the concepts together, we get to update the predictions accordingly. Note that here we no longer have concepts x's and y's, but also this logit space. And this is because we're modeling the distributions in the logit level, because this is a continuous variable, instead of the concepts that we are assuming binary 0, 1. Apart from the fact that, well, this prediction makes more sense, this allows us to speed things up, so you don't have to intervene on both, but just on one. How do we do this? So we model these logits I was mentioning as Gaussian distributions whose statistics, so the mean and the covariance, actually are learned through a neural network. The fact that they're Gaussian allows us to have closed form interventions. So you can get the updated logit of the non-intervened on concepts. This is actually counterfactuals, they say not interventions, but in the CBM literature, we can say interventions. How do we learn this? Well, standard way, negative log likelihood. But because we have the distributions and the binary concepts, we actually need to do Monte Carlo integration. This covariance I'm mentioning here, as you see, it's parameterized by X or amortized by X. But you could also think that the covariance is global to the whole data set. So we actually tried both things. So one, you amortize it with respect to your input sample, and another one, you learn it globally. This is just the loss, but in a nutshell, same as always in CBMs, you supervise the concepts, let's say classification on the concepts, you supervise the final target, and what we do is that we also impose some sparsity on this covariance because we wouldn't want to have spurious correlations or very low dependencies. And how do we intervene? So since we have this logit space, it's not as easy as saying 0 or 1. The common solutions from the CBM literature would be, okay, I set the logits to the 5th or 95th percentile of the data, or I directly do the inverse of the sigmoid to 0.05 or 0.95 probabilities. But in our case, since we're modeling the whole distribution, this could actually have shifts that we do not want. For instance, if the logit was actually bigger than the inverse of the 95 probability, then we would be moving things in the opposite direction. And because of this, we actually introduce a way to intervene or update your logits given this distribution. So to understand it a bit better, I will motivate it with a 1D, so normal Gaussian distribution, and then we'll see how this turns into the multivariate distribution. But let's assume we have the confidence interval, and in here, if we were to set actually the logits, then the shift would always be in the correct direction. But in the multivariate space, instead of that, we now have the confidence region instead of the interval. And for this, we want to be able to intervene, but on which point? So we propose to maximize the actual corrective effect. And this translates into having a constraint so that you are actually within your confidence region. This formula here stands for the confidence region, and that the direction is correct. By doing this, we actually kind of are able to propose interventions that capture more the natural range of values and that are faithful to your distributions. Taking, of course, the correlations into account. So this is something positive that comes out of modeling your distributions. I will now show you the results. The main results were on a synthetic tabular data set and CUB, that is birds with a lot of concepts, being the color of the body, the head, or many more. And we also added a setting which at the time was starting to be novel. Now it would be quite standard, but it's the fact that since you need all of these annotations, you could leverage the vision language models to give you the annotation. And since this would point more to this concept discovery literature, there's been multiple papers doing it now, but at the time, this label-free CBM was one of the first ones. You can just find the concepts using your GPT or whatever language model you want, and then label them with CLIP or now any other image to text labeler, and that way you can actually also get annotations on other data sets. So we were then able to do it on CIFAR 10, and you could do it on any image you can think of. What are the results of this? So one could think, okay, you're modeling this distribution, but are you actually then still faithful to the performance? Well, yes, the test performance remained on pair. Here the bold is the best model, and then the underline is second best. We compare with the concept embedding models that are quite state of the art in CBMs. Then hard CBM, because as you saw before, we have binary concepts. So this means instead of having your probabilities, you actually have 0 ones. And autoregressive, because at the time it was the only one that was also modeling these distributions of the concept, but in an autoregressive manner. So let's say connections, skip connections between the concepts. And we also showed here that this autoregressive one that was doing something similar actually takes a lot longer time at inference, because as I said, you need to go kind of through the whole chain in an autoregressive manner, while we directly have the distribution there. And the results that I wanted to get to are that we actually are better or can do interventions faster. I will briefly explain these plots because in the next paper I'm going to present, we also evaluated this way. So the first row is the concept accuracy, and the second row is the target accuracy. And what I want you to take home from here is the steeper the curve, the better, because this x-axis would be the number of concepts you're intervening on. So if you're able to get the performance intervening on less samples, this means you're most effective. So the key here is that the green and the red are actually the steeper curves across data sets and baselines. And this means that with the interventions, you are most effective, since remember the head and the body of the fish, you can kind of do it all at once. And the two different colors are whether you do it globally or amortized with these covariants. Overall, both were working, but we saw that if your data generating process is global, using the global one would help, mainly in the synthetic experiments, and otherwise data specific is better. But what else do we get from this modeling the distributions? Well, there's a side outcome that was also quite interesting, is that since now you have your distribution, think of this here, both sides of this matrix, where the matrix is the covariance, as concepts. So we found a lot of patterns in the data. In this data set example, it's quite clear because the concepts are very grouped by color, by body parts. So we saw that actually when you find these blocks, it means these concepts are correlated, and this could allow you to find patterns in your data and understand it better. So this is a bit, let's say, a way to tackle this limitation of assuming independent concepts and still being able to use CBMs. And we just briefly also showed that the actual calibration of the model is improved based on the Briere and the ECE scores. And calibration improved usually means, okay, your uncertainties are more reliable. And we also tried to do these curves I was showing based on the most uncertain concepts. And indeed, we saw the two steepest come from just intervening on the most uncertain ones. And this is better than random and makes sense if you are properly calibrated. So these are a bit the results. And we recently also extended this with a very simple idea, that is, you need to train this model, this multivariate distribution, but what if I already had a CBM? Well, we showed that you can also train it post hoc, meaning this top part here would be your regular CBM with your X's, your concept predictor, and then your sampling, and you have the final target. And what we do is we just learn a covariance module post hoc, and we show that this green here is this SCBM, meaning the stochastic CBM. If we could train it from scratch, it's generally better. But if you have your CBM, which is the blue one, by only learning this module, we are actually able to improve significantly close to the green one. And this I is just modeling also the interventions in the training pipeline, but for more details, you can take a look at the paper if you're interested. And well, so it is a boost in your intervention performance if this is what you are looking for in your model. Now that I've talked about this limitation, I want to introduce another work that here I refer to as beyond CBMs and annotations to ensure intervenability. So since I said before that we are restricting ourselves to this bottleneck in the middle, and also we need a lot of annotations, what we try to do in this work is, what if I have a pre-trained model? I have already a backbone that I trained on a lot of data, and I want to now kind of inherit the CBM capabilities to intervene and to get some understanding, but I don't have the capacity to train everything again from scratch with the concepts. So given that at training time you didn't have annotations of the concepts, or now you just don't have capacity computationally to retrain it from scratch, but you still want to collaborate with the model, as I was mentioning, we came up with, we proposed a way to actually intervene on these black boxes. How? So imagine that this now is not a CBM, but just any neural network or any backbone from which you have some representations at the output space. So what we do is we want to be able to predict the concepts and also intervene. So if I'm predicting here these three different concepts, in this case, this is a zebra, and I know it because I'm very smart and I know the types of animals, but it could be that it's a very challenging task and it's not so trivial to classify it out of the box. But I do see that in here, it says no stripes and my image has stripes. So the goal would be to kind of update these with stripes and then get the correct output. As a pointer to make it motivated a bit more, this is mainly important in high stakes decisions. So think of healthcare or any other situation where you need this human model collaboration for reliability, and you want the human to be able to intervene or to input information. So how do we do it effectively? Here you have a neural network, as I mentioned, and a validation set. So we do need some annotations of concepts, but it can be very small. And later on, I will show you how small actually this can be. The idea is that, think of the model before from the zebra. We can do this probing and intervening in 3 steps. One is that you first learn a probe. A probe really can just be a linear MLP layer, whatever you want, from your representations onto the concepts that you have in your validation set. The second step is, well, now I have the mapping from set to the concepts, but how do I update my output? Well, we want to edit the representations being this set. And here, this is just an illustration of what a representation could be. And how do we update it? Well, you can try to find the new representation in a counterfactual-like manner. So what is, like, I want to try to minimize the distance. So find a representation that is as close as possible to the original one. So this red part, we would like to minimize it, but that indeed gives you the correct prediction through the probe I learned before. In this way, I can now actually update my representation given this intervention. So I want to find what is my new representation if I now change to stripes. With this counterfactual-like optimization, it's very quick and you can directly get your new representation. And once you have this, you just update your output. These are very simple steps, and the results were looking promising, and it was actually the predictions were getting improved. But there are times in which maybe your model has just never seen these other representations, and it's not so good at like propagating them downstream. So for this, we try to think a bit about what intervening actually was, and we formalized, or we proposed a way to formalize this intervenability. You can think about it as trying to have that the distance between my loss in the original input and my loss after this intervention is as big as possible. And this would mean that my updated representation actually has an effect, and it has an effect ideally in the correct direction because my loss is pulling me down. So this metric can be added to your regular loss. And I don't want to bore you too much with the optimization details, but in a nutshell, you can simplify the loss so that you only have to update your downstream not the backbone, but the downstream predictor. And we did see how for different data sets, here also including medical ones that are a bit more complicated than the previous ones I showed, and also with this VLM style of labeling, we actually get very good interventions. So again, as before, in these curves, the steeper, the better. And in the pink ones, we see that with this method that has been fine-tuned for the intervenability, we actually are steeper, and we can therefore just work or have an effect on the models that before, without this CBM, like, you could not. So the human could not input this data at inference time, and now we can. This is an example just to see that the validation set can be very, very small, up to 0.5% of your normal training, let's say. So you really don't need so much because effectively you're just learning a probe and updating the representation. And again, the calibration actually was improved of this of the original model if you compare it as well with a CBM. These two have been, let's say, the biggest papers I will talk about today. And now I just briefly wanted to also touch upon another smaller contribution or smaller work that was trying to tackle the limitation of this leakage. Or remember, I showed a residual channel because there's some information that is also going through. So we were trying to formalize this. Yeah, sorry, I forgot I had this. So this is the channel I was talking about here. So intuitively, what this channel means, or what this leakage is the amount of extra information that is contained on your prediction of the concepts when this independence assumption is violated. How do we formalize this? So we propose the following way. Given a neural network where you have, again, your concept being predicted, the goal is to compute the information that is in the prediction of C that is used for Y, but is independent of the concepts. For this, you can just have the mutual information. So let's say, what's the mutual information of Y and the concepts predicted, given the actual concept? And the mutual information can be written as the difference in entropies. And actually, the entropy, you can really just approximate it here through a neural network that actually takes in the corresponding inputs. And Monte Carlo sampling, you just do a lot of predictions. And with this, you get not analytical, but an approximation of your entropy. And what we propose is, what if we now use this metric to show how much leakage your model had? And this could be used as a way of a sanity checking of models, or even just a way to decide which model to use if what you care about is the purity of your concept prediction. And we actually evaluated it on synthetic data, on just a predictor. In this case, as you go towards the larger values in the x-axis, we are expecting less leakage, and it is the case. Why? Because this B is the number of features that you use in your ground truth concepts. So let's say that if you have, this is a data generation that we proposed, a synthetic data setting, and if you actually have all the ground truth concepts as inputs, then there's no leakage. And this shows that with very few concepts, of course, there's a lot of leakage because all of the capacity goes for leaking. But if you actually define more of your points to be concepts, then that's fine. And then we also tried it in a normal CBM setting where this lambda here is your weight in the loss between the concept and the target. And so the bigger the weight on the concepts, you expect less leakage because the model prioritizes this learning. And indeed it works. So with this, we wanted to propose like a validated and formally formal way to actually evaluate your models if leakage is what you're caring about. And then I have also two smaller things, one more these applications of the concepts. And let's say we have these concept bottleneck models that are very nice because they give you interpretability, but what else can we do with them, or what applications do they have? So one of these works is leveraging diffusion models to understand the information in the concepts. So as you may be familiar with, we have diffusion models that can generate conditionally. So if you think of classifier-free guidance or any of the other diffusion models, you're trying to go from noise to a generation, but you can steer it or guide it. So what we do in this work is, what if actually we try to generate based on some concepts? So instead of, usually you would steer based on a class, but these concepts are now a multi-label setting, right? It could be that multiple concepts are present, or some are maybe unknown, or some are not present. So what we do here is we try to kind of rethink the classifier-free guidance for the concept setting. And we actually, well, in this work, we actually also do it for prototype networks, but I think it's out of the scope for the presentation today. You can take a look at it if you're interested. But what we do is we condition based on embeddings, the same way that usually diffusion models have time positional embeddings. And in this case, we also have positive, opposite, or double embeddings. What does this mean? So we define now an embedding that, as you see here, instead of just one unit, it has, instead of just one, it has as many rows as concepts. And then we have a mask that says, which concept am I actually using? And then here, the positive embedding just tells me, I want to generate from this one. If instead you want to use the opposite embedding, that actually tells you which one you also don't want to have, we propose in this paper how to model this. And then we have a double embedding that allows you to condition multiple things. And we actually saw that it works really well. So if you say, I don't want black wings, but I want white belly, you get generations that look a bit like this. And well, here red means not want. And well, it works for different combinations as well as for multi-concept generation. So you can get new generations given different concepts. And this is nice because with this new idea of classifier-free guidance, we can actually augment the data sets that need concepts. So imagine that before we said we don't have annotations, you could try to generate a data set that you are just defining what concepts you use. And this can be helpful for other CBMs or for other models. And you can also try to visualize abstract concepts in data sets. So this is a bit of a, let's say, side project that is not directly in CBMs, but that can be leveraged and that can be applied for CBMs. And then finally, I see that time is not so much, so I'll maybe skip some parts of this one, but I wanted to show also an example of how CBMs are not only used in discriminative tasks, but can also be used for other, let's say, bigger or more foundation models like nowadays are more present. So in this case, I want to focus on this RLHF or an LLM setting. For those of you not familiar with RLHF, it's a very simple idea for aligning LLMs where you have your reinforcement learning algorithm that is, of course, working in an environment. And it's doing some actions in it, and then it observes. But apart from this, you also have a reward predictor. So a model that tells you whether your generation or your text is better, is like it gives you a score. And this score has been trained with human feedback where you have a prompt and two answers, and a human has said, this answer is better than another. Why am I talking about this now? Well, in this work, we actually replaced, or let's say that the bad side is that this reward is a bit, there's a lot of issues with the fact that maybe it just measures how long the response is, or there's a lot of confounders. So it's not interpretable. So in this work, we try to actually turn these reward models into interpretable models. I will, here I posted a bit the formalism of it, and I'll just briefly let it here so that you can read through it if you want, but the important thing can be seen in this figure, where you have one prompt and two responses, as I mentioned before. And usually you would pass these through your reward model and get a score saying one is better than the other. And instead, what we have done is predicted some concepts that are also text in this case. So since we are talking about responses, we can say what's the helpfulness, what's the correctness, coherence, realism, or if this was coding, you could say functioning or whatever concept you want. And the idea here is that you now have these concepts that can be then used or passed through another layer. Look at this formula here, shows that this is just a linear layer. And in this case, we predicted the weights through another function so that the weights actually depend on the prompt, because this is the case for text usually that your answers are depending on your actual prompt. And what we just did was, okay, now we turn these reward models into a CBM-like fashion. And why is this, or what else did we combine this with? So we would need a lot of annotations. Annotations are very expensive. So instead of just having all these preference labels from humans and also annotated, we propose to add active learning to the CBM. This is also a bit of a contribution because there's not so much work that has been done on this active learning side on knowing what sample to label and to give a concept from. We use this first in, first out replay buffer. And what we actually did was explore different acquisition functions. So for those of you not so familiar with active learning, this CBRM is the reward model that would give you would have some prompt and response pairs. And for each one of these, you would need an annotated concept. So what we do is we start with a little bit of data that is annotated, and then you get the prediction of the model, and then based on some acquisition function, which is some score, you decide which concept to label. And you can do this in multiple episodes to get more efficient training. So what we did in this work is we explored different acquisition functions, and I will not bore you with this, but in the end, we saw there was one that was working better than others, in particular based on the expected information gain. So since we have the CBM, we have concepts and whys, and we can now model the active learning part as what are the concepts that will give me better outcomes, given all the possibilities, and also knowing that we have the concepts modeled as distributions as well. So you can ask me questions afterwards if you want, but the conclusion was that with these new acquisition functions, we could actually same plots as before, but now a bit of different because it's not interventions. With less episodes, we can get faster improvements in the accuracy. And the conclusion of this is that we actually also introduce CBMs in these LLMs, and it's very sample efficient, and it's another contribution. So to conclude everything, sorry, I ran a bit out of time, but I introduced to you again what CBMs is, although most of you knew that probably. I mentioned different limitations and ways to tackle them. One of it was assuming that the concepts are independent. For this, we propose modeling the concept distribution. Another one is the fact that you need a lot of annotations and you're constrained to the bottleneck model. And for this, we kind of proposed a way to intervene on black box models. Then I also touched upon the fact that these CBMs give certain assumptions that then lead to information leakage, and we proposed a way to measure it. And I introduced different ways or applications that the concept literature also allows. So thank you very much. I'm super happy to hear your questions. A bit about me, as I mentioned before, I'm a PhD student at ETH Zurich. I've done different stays and internships during my PhD, and I have worked quite a bit on interpretability from what I presented today, but I also I'm interested and have different works on representation learning and also machine learning recently, as well as some generative models. I'm happy to take any questions, and I hope you learned something today. I see a question already. I'm not sure how.
Yeah, thank you for the presentation, Sonia. And yes, if you have questions, unmute yourself and just ask. I see Arianna had a question.
No, sorry, I wrongly clicked the button. Sorry.
Oh, no problem. Otherwise, I can start. Oh, Sonali. Go ahead.
Yeah, I don't know if this is the right way of phrasing this question, but something that bothers me a lot is this notion of interventions in like concept bottleneck models versus interventions in like causal models and in the causal sense. And just this last section that you were presenting on RLHF, where you do this kind of active learning loop, it really reminded me of we've got a lot of work on causal Bayesian optimization and kind of updating priors on beliefs about what causal graphs might look like. And so I was wondering if like we could think about in sort of concept space, maybe you have like you don't have a concrete notion of what the causal graph might be, but you have some concepts and you know roughly how they are dependent on one another, and maybe some sort of like notion, and that could constitute a prior. And then you could do kind of this active learning loop to kind of ascertain how that graph structure, that rough graph structure, should be updated, which is exactly what you're doing in this active learning, right? But you're doing it for the reward model specifically. But I'm just thinking more generally. But now, when you're intervening in an active learning sense, it's usually the reason you have this acquisition function is basically because you choose the most informative intervention actually to do, right? And then when you do that intervention, you're actually changing something in the causal graph. So now I'm a bit confused as to like, okay, is your intervention then in the active learning framework that you've proposed for the RLHF story, is that doing an intervention in a causal sense, or is it doing an intervention in like a concept bottleneck sense, right? Is it really active learning? Is kind of what I'm struggling with.
Yeah, I see your point. I think it's a very good point. If anything, I think I mentioned also at some point like intervention count, like note this is the CBM literature kind of approach, because I do agree with you that terminology even it's a bit tricky. I myself am no expert in causality, but I think actually probably some members of the audience today, there's been work proposing these graph CBMs, or kind of modeling actually the graphs or even the causal relationship in them. So I think if you frame it that way, I mean, of course, it's way closer, and you could still talk about interventions. But I think for that, you might need some guarantees that I'm not sure of, or that the regular CBMs would not give you. And in the more active learning side, I mean, from my point of view, since we're all in that project in particular, I'm again framing the concepts as separately, right? We are not kind of making connections between them. So because of that, maybe we're not really changing that much the, let's say, what the causal relationship would be between them. And I think it is quite, or let's say these interventions are like the CBM literature, but I do agree with you that the fact that you need to, let's say, intervene, not for a better prediction, but for a better effect in the training. This changes things a lot.
Exactly.
For that, you do need to define acquisition functions differently. So I actually tried to, like, there's a lot of literature on the intervening. So I tried to get inspiration from there, but that doesn't work directly because you want better training, not better inference somehow.
Exactly.
But I think it is still within the CBM side, and I would not put it together with causality, just in the way it's framed right now. If it makes sense.
Yeah, it's a confusing question because the terminology is very similar, but I see the distinction, and that's why it's like active learning. You can do active learning in both senses. Like the CBO literature does a lot of active learning with certain acquisition functions, and then you learn priors of the causal graphs and you update those. But this is just doing it in a CBM framework, which is doing something slightly different. And then the meaning of active learning as well. It's not like active learning in the sense that we do an intervention, like a causal intervention. It's a different kind of intervention.
Yeah, but it's a very good point. I honestly wish I had more time to allocate to that project to continue making it bigger, but it's, yeah, I haven't had the capacity. But I think the key would be whether you model these concepts together or really just separately. Again, I think modeling them independently is a challenge by itself, but like you can only tackle things from one side at a time. But it's a very good point. I fully agree.
Thank you.
Yes? I think, Akshay, you are...
Yeah, hi. Thanks for the great talk. So I had a question about the part where you discussed concepts to be like modeled together instead of independently.
Mhm.
So there's also like a concern where, let's say two concepts are correlated and you intervene on one of them,
Mhm.
then like the other one also changes, which is like one of the examples that you showed with the fish head. But so like there could be another perspective where that might be desirable to have only one concept changing and not the other. So what are your like thoughts on that?
Yes, so I agree with you. I think by modeling them together, you kind of allow for, let's say, more automatic, faster interventions. But if in particular you really wanted a fish head and a body of the human, you can like you allow to intervene a lot of things at the same time. So you can intervene on negative, positive. And so then let's say that you can fix whatever you want to have fixed and then let the other ones be free. So that's a bit
I
my
see.
take. Like if you really want to do things that are outside of what the model would be most likely to do, you can just intervene on both things at the same time. And this would still work because you still have a set and you only update the non-intervened given the intervened. So those remain fixed.
Okay, thank you.
Have you ever tried switching, like to build an automatic switch between the two modes, like a switch that allows SCBMs to either behave like an SCBM, so modeling the relations between concepts and use that to make intervention faster, or a switch that allows you to intervene on just, and if the switch turns off, then you have like the standard behavior of CBM that if you intervene on one concept, nothing else changes. Like something that switches on and off automatically the...
So I haven't, but I guess you could just replace the covariance by a diagonal matrix, right? And then that's it.
Yeah, that's something like that. But is it something that I'm wondering whether something like that during training could allow the model to respond better to these two kinds of interventions.
Yes, I see your point. No, to be honest, we haven't looked at this, but I think it's a good point. Also, the fact that it could be that you want something that is a bit out of the not out of distribution, but this fish head and body, and with the model by default we don't allow it. But something you could also do maybe is like impose even more sparsity so that only the things that are super like very strongly related update and not so many things. But still, I think if in the current setting, if you want to do it, you just have to define the intervention and that's it. But it's a good point. I mean, another thing that one could do that we didn't do that is now done in this post-hoc CBM is to actually train with the interventions. So since you already know that you're going to intervene afterwards, if you model them during training, then you allow for these different distributions. So this we did in the post-hoc CBM, and it improves the training. That was, I don't know, the yellow curve was a bit steeper, but you could do it, and maybe you could even define in which way you do these interventions at training, and this would affect them. So if you really want this, maybe you could do the interventions in these different ways at training time and then update it.
Thanks. Yeah. Are there any other questions?
I might have a quick one if we have time. Do we? It's 4 minutes.
I think so, 4 minutes.
I will try to be quick. So thank you, Sonia. Just a quick question on the conditioning of the diffusion model with concepts.
Yes.
So 2 quick questions. The first is, do you model also correlation between the concepts in that scenario? Because if you, for example, if you introduce the concept of wings, would you still have a peak in some sense, or does it have the same correlation of stochastic CBM, or at that point you try to maximize independence? You're like, I only want that concept in and nothing else.
Yes, I guess I should have made this clearer, but no. So the only part where we are actually modeling the dependencies is in these first 2 main things I mentioned of SCBM, Afterwards, all of the others are more on the independent side. But in the one for diffusion, actually, it's quite interesting what you're saying of what if like you want also a head or a pig or whatever. Since it was trained on the full data, let's say on birds and everything, even if you only condition on wing, it's still gonna, it's quite, I think it's nice because it would still give you a bird, but it would just be that that wing is yellow. But you do have the whole data distribution that you trained on, of course. And if you want to have both things, you just need to condition on multiple. There's no automatic update there. How you could do that, I would need to think about it, because you would probably need to have also embeddings for conditioning and so on, which scalability might be a bit complicated there.
Yeah, I see. And have you tried to see if some performance improve after you augment your data set with such techniques, or comparing to simple data augmentations like any other data augmentations? Is it more grounded in reality or something like that? That would be interesting to see if you can really boost some metrics.
Yeah, that's a good point. And no, we didn't do that. So that project also had more prototype-based methods. So we were trying to also generate prototypes of concepts, and it was more focused on visualizing and kind of.
Okay, it was just a visual check.
Yeah, and to be fully honest, the motivation for me was I wanted to try to visualize or to find what the concepts that are not so tangible for us, like what these abstract concepts would actually show. And that's why we didn't actually do the downstream. Like, this was through a student, and then eventually difficult to follow up. But I think from the data we saw being generated, you could just really generate as much as you want. It's a diffusion model, and then fit CBMs there and see how it works.
I see. Thank you very much.
Yeah, of course.
Sorry, I have one question from someone online. Yeah, I'll just read it. Asking whether optimizing for interpretability make the model more susceptible to adversarial examples. Whether you think that's the case.
We just have less than a minute, so.
So very quick.
Personally, I would not think so. If anything, it's less susceptible because these interventions could be a bit adversarial-like. So I don't think it would make it more susceptible to them.
Sorry, but I think the meeting is about to end. Thank you, Sonia, again so much.
Thank you so much for inviting me as well.
And see you next week.